record. Okay, so we've gotten to the point where we've introduced linear systems. It's a set of equations or a list of equations with one, two, or more variables, and we're looking for the set of all the solutions. And a solution of a system with two variables is going to be a pair of numbers. The solution of a system with three variables is going to be a triple of numbers. And if he has four variables, it's going to be a quadruple of numbers, or because you have an arbitrary number that you call them tuples, which is sort of a weird word. And it comes from the sound of the last syllable of the word multiple. And you have like a three tuple or a four tuple. Okay, well, let us go on and see, how do I solve a linear system? Well, there's a method called Gauss's method. And this is the heart of chapter 1. And your first assignment is applying Gauss's method to solve linear systems. So let's write down a linear system and let me show you how it works. And as an example, so let's try 3x plus 6y equals say 9, and 6x plus 3y equals 6. Okay, I have no idea how complicated or simple this solution is. Now, you may have you may have seen a system like this in high school or some other algebra course. Solve this by a method of, say, solving for one of the variables and then plugging in that variable to the other one and then solving for the other variable. We're not going to use that method. That method doesn't work when you have like 4 equations and 5 variables or something like that, because the algebra gets too complicated. So we need to transform. Gauss's method is a way of transforming any linear system into a special form that is easy to solve by solving for one variable then solving for the next. Now, Gauss's method, first of all, this is a standard form for the linear system that we'll always use. The first column, the variables are all lined up, and we'll put all the variables on the left. And this part here is called a linear combination. The reason this equation is linear is going to be because it only has first powers of the variables. So for example, 3x squared plus 2y equals 6 is not a linear system, because the variable doesn't come in with the first power. The only variable powers that can come in are x's or y's. You cannot have x to the minus 1, 1 over x, x cubed, any other power, or you can't have like xy terms. So this is called a linear combination, which you just have a number. This is a term with just, this is sort of a term with just the first power, just one variable. You can't have two variables. And then it's a sum of those variables. That's a linear combination. So a linear equation is just a linear combination equals a number. So we have these two linear equations, and we want to transform it into a simpler system. And we can only there's only 3 operations we can do. There's lots of algebraic moves you can make. For example, we're never going to switch the order of x and y. That's not an allowed move. So Gauss's method is a set of allowed moves, and they're called row operations. And there's only 3 of them. The first one is I can multiply a row by a non-zero number. What that means is if I wanted to multiply this by a number, I could, I could do that here. I'm going to write, what you do is you then write down the whole system again, but I'm going to multiply the first row by say 2. So I could get here 6x plus 12y equals 18, and then 6x plus 3y equals 6. So I multiplied just one row, the first row, by the number 2. Well, that's an example of this first row operation. So I can multiply any number by a non-zero number. If I can't multiply it by 0, because if I multiply this equation by 0, it would just remove that equation from the system, and then it would change the number of solutions. Or it could change the number of solutions. So I can't use I can't multiply by 0. The second one is I can swap rows if I wanted to. I could like exchange. This is a list. This is first. This is second. I could change the order of the rows. Okay, that's the other move I can make. The third and last one is the most interesting, or the one that sort of gives this thing all the power. Is I can add a multiple, of one row to another. Okay, so I could multiply this by say -2 and add it to the second row, and that would, and if I did that, let's do that here, where I'm going to, now you don't change the first row, because even though I'm going to add 2 times the first row, I don't change the first row. So I just repeat, well, I'm going to add 2 times this to the second row. Well, I can do it term by term. If I multiply this by -2, -2 times 3 is 6. So this is going to be -6 plus 6x is going to give me 0. X plus -12y plus 3y is -9y equals, I have to then do the same thing on the other side. -2 times 9 is -18. -18 plus 6, I think, is -12. Okay, so do you see what I did there? I didn't change the first row, but I added a number, -2 times the first row to the second row. That's the third operation. This one's, we call this the row combination operation. This one's a row swap, and this one is a row rescaling, or scale. It's like a scale is like sort of like, anyway, that's just the term that's used for other reasons we'll see later. Okay, so what's the goal of this? The goal is to put this thing in a form called echelon form. So I'm just gonna rewrite this without the 0 here. So this is just rewriting it. So this one row operation transformed this system into this linear system. Okay, so the claim is, if I restrict myself to these 3 row operations, the transform system here has exactly the same solutions that the first one does. The same is true over here. Okay, so so the row operations, there's a proof that guarantees that there's no new solutions. You don't like introducing new solutions, and you don't lose any old ones. So if I solve this system, I'll find all the solutions that were in this system here. Now the goal is, is to have something that's called echelon form. That's the target operation, echelon form. Now, echelon form means that as you go down from one row to the next, the leading row the leading term in each row. So example, for example, up here, the leading term here is 3x in the first row. The leading term in the second row is 6x. Well, to be an echelon form, the leading term in each row has to have nothing underneath it. So therefore, this is not an echelon form. But this is an echelon form here because this one has nothing underneath it, right? And this one, well, there's the last equation, so it also has nothing underneath it. So that's the goal, echelon form. And it's like this only required one row operation, but if we had 3 variables and 2 equations, or 3 variables and 3 equations, you might need to do more row operations to put into echelon form. And we'll see that later. Basically, echelon form means that if you look at it, the leading term in each row is to the right of the one above it. So it sort of forms a reverse staircase. That's echelon form. So once you get to echelon form, that makes it's simple to solve the system by the algebra of back substitution. That's what the method is called. So basically, Gauss's method is you use row operations to get to echelon form, then you do back substitution. So that the strategy is you start with the top row and make all the rows underneath the first term 0, and then do it with the next row down as you go on. And then at the end, you start from the bottom and move back upwards, the opposite of the row that you produced echelon form. So here, what I do is back substitution would involve solving the last equation. And since it only has one term here, I can solve it right away as y equals 12 over 9. And I think that's 3 times 4 and 3 times 3. So I think that this is 4/3, okay, to reduce it to lowest terms. So then I can take, and sometimes you don't, it's not necessary to reduce it, because sometimes, like here, it's actually going to work to leave it in this, well, maybe it's better to leave it in this form here. Sometimes it's better to leave it. Okay, so what you do is you solve the bottom equation for y, and then substitute that back up in the previous equation. So this was our solution of the bottom equation. Then we got the top equation that we have to solve, then becomes 3x plus 6 times 4/3. You plug in the value for y, which equals 9. And then we can solve this for x, because it only has one variable, because since I've eliminated this y variable here, this is going to be plus 2 times 4 is 8 equals 9. Subtract 8 from both sides and get 3x equals 1, and then x equals 1/3. So I found that y equals 4/3 and x equals 1/3. So this system only has one equation. So we're going to record the solution as the solution set equals. Now, the order of the variables, the parentheses here mean ordered pair, so the order matters. So the order of the variables here is always the same as the order of the variables in the linear system, and we never reverse them, because Gauss's method doesn't allow us to do that. And so just from writing this down, we know that the solution is x is 1/3, y is 4/3. Okay, so any questions? Oh, well, no, I don't want to do that. I want to go back